One of the main ideas in Chapter 10 has to do with a quantity like this. The square root of 3 is kind of a strange number. You can get a decimal approximation by doing the square root of 3 on a calculator, and it'll be 1.7 something or other. But the square root of 3 has a meaning. It is the principal square root of 3, which means the positive square root of 3, which means this is a number that you can multiply by itself to get 3. And we might not be sure what decimal number that is, but we do know that if you take this and multiply it by itself, you have to get 3 by the definition of what it means to be the square root of 3. In the same kind of reasoning, as long as x isn't negative, the square root of x is something that you can multiply by itself and get x. This is not the result of a calculation. This is the result of a definition. Cube roots work the same way. The cube root of 7 is some weird decimal number just a little smaller than 2. If you know how to key it in on the calculator, go ahead and key it in. But the thing we do know about the cube root of 7 is that if you multiply 3 of them together, 1, 2, 3, multiply together, you get exactly regular 7. That is the key fact. So how many 11th roots of 5 would you have to multiply together to get exactly 5? How many of them would it take? It would take 11 of them. You'd have to multiply 11 of these together to get 5. All right, so that's the background for what comes next. What comes next are a lot of different kinds of problems, one of which is to take something like the square root of 145 and simplify it. This is kind of a basic sort of problem, so let's take a look at what we can do. First of all, we figure out what is the prime factorization of 145. 5 goes into 145. It goes in 29 times. And so we have that the square root of 145 is the square root of 5 times 29. The square root of a product is the same thing as the product of the square roots. You can always do this. If you have the square root of a multiplication problem, you can always break it apart into a multiplication of the square roots. Now, what do we know about this root 5? We know that if you have 2 of them multiplied together, you get 5. And we know if you have 2 of these multiplied together, you get 29. But we don't have 2 of either one, so they're both kind of isolated or left over, and we generally leave them in one leftover bin. And so if we put 5 times 29 in here, we get 145, and we haven't made any progress because this is simplified already. Now let's take a very similar looking problem and try it. We're going to do the prime factorization of 175. 5 goes into it. 5 happens to go into it 35 times. 35 is 5 times 7. So we have that the square root of 175 is the square root of 5 times 7. But the square root or root of a product is always the same as the product of the individual roots. And now look at what we have. Square root of 5 is a number you can multiply by itself to get 5, and we're busy multiplying it by itself, so that's just exactly 5. And this piece is left over, and we're done. So keep in mind those couple of different ideas. Now let's move on and try one that's a little bit more involved. There's more stuff going on here. Let's try the square root of 180. Let's simplify it. And so we have 180 equals maybe 10 times 18. 10 is 2 times 5. 18 is 6 times 3. We've got 2 times 5. 6 is 2 times 3 times another 3. That's 2 times 2 times 3 times 3 times 5. So the square root of 180 is the same as this. And now we can break it apart because the square root of a product is the product of the square roots, always, as long as you're dealing with positive numbers. This times itself makes a regular 2. This makes a regular 3. This piece is left over, and we have 6 times square root of 5. So let's try a problem that's sort of similar, but let's put in some variables just for the fun of it. So how would we simplify this? First, we would break all the pieces apart. And then we would rewrite it using separate roots. This can get a little bit dull when there's lots and lots of parts. But I've got the 3 2's, the 3 x's, and the 4 y's. This makes a regular 2. This is left over. This makes a regular x. This is left over. This makes a regular y. This makes a regular y. No leftovers. The leftover pieces of a 2 times an x go in one leftover root bin, and we have 2xy squared times the square root of 2x. And we're done. This is the best way to do these problems. If you go to a tutor, you're going to get some other things that they think are shorter. But just trust me on this. This is the way to learn how to do this. It has many, 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 many good consequences for you. One of them is, if you start going with cube roots, it's the same sort of process. It really is. You still have that 175. You still have it being 5 times 35. And you still have 5 times 5 times 7. And now it's the cube root of 5 times 5 times 7, which would be these cube roots. But how many cube roots does it take to get the thing inside? It takes 3 of them. It takes 3, and you only got 2. So these are left over. These are left over. You got to put them in one leftover bin, and you're done. So let's try one where maybe there is something outside of the leftover bin, just to have something to look at. Let's say we've got 16x to the 5th, and it's the cube root, and we want to simplify this. Well, 16 is 4 2's multiplied together. X to the 5th is 5 x's multiplied together. This is a lot of parts. Takes a little while, but it's worth getting this drilled into our brains. And if spending a few seconds doing this drills it into our brains, great. It is a little dull though, so there we go. The cube root of a product is the product of the cube roots. It takes 3 of them, so there's 3 of them. That makes a regular 2. Here's a leftover. I'm going to circle the leftovers. It takes 3 of these to make a regular x. These are leftover. I'm going to circle the leftovers. Now I put all the leftover little cube root pieces in one leftover container. So I've got a 2 times an x times an x, or an x squared. And so this is 2x times the cube root of 2x squared, and I'm done. And that's not a bad process. It's just not. So now let's do some problems. There are many ways to do this problem, but I would break apart the numbers. There's a lot to be learned. This will teach you a lot of things. 40 is 2 times 2 times 2 times 5. 10 is 2 times 5. So this square root of 10 breaks apart into the square root of 2 times the square root of 5. This square root of 40 breaks apart into these pieces. And now let's try to find pairs. 1, 2. Those make a regular 5. These 2 make a regular 2. These 2 make a regular 2. 10 times 2 is 20. This is 20. There are other ways to do this problem, but they're for people that have a really strong background in both arithmetic and algebra. And the way to get that strong background is to start playing with these pieces, in addition to which playing with these pieces is the safest way to get right answers on an exam. Now I gotta tell you, if you had something like this, I suppose that you could, write down 51 of these. But I have no desire to write down 51. So by the time you encounter problems where there's too many pieces, you're supposed to be able to handle it on your own. So if you had 51 pieces, how many pairs would you have and how many would be left over? Well, 51 divided by 2 is 25 with the remainder of 1. So if you had 51 of these guys, the first pair would give you an x, the next pair would give you an x, and in fact you'd have 25 of them, so you'd have 25 x's. That's x to the 25th, all right? And then you would have one little x left over in the bin. And so the simplification of the square root of x to the 51st would be x to the 25th times root x. And we can kind of just imagine writing them all out. So the idea is to write them all out when it's possible. And when it's not possible, the idea is to do this kind of thinking. So let's try another one. Let's try the cube root of y to the 13th. Now we could write out 13 of them. We could, and we probably should, and then we would group them in groups of 3. But let's see if we can figure it out. How many groups of 3 will there be in y to the 13th? Well, how many 3's are there in 13? There's 4 of them with the remainder of 1. So the first 3 of them, that'll make a y. And the second 3 of them, that'll make a y. And so it'll be y to the 4th times the leftover cube root of y. If that's moving too fast for you, then go up to this kind of behavior and do this. And keep doing it and doing it and doing it until this faster thing makes sense to you and you're rock solid at it.